We learned that significant figures are numbers in a measurement that carry information. So if you as a scientist go into the laboratory, measure some quantity with some device, when you record that measurement, you need to be able to tell me how many significant figures are in it. So let's go over the rules for counting the number of significant figures in a measurement. Non-zero integers in a measurement are always significant. What are non-zero integers? Well, they're essentially 1 through 9. So for example, 356 centimeters would have 3 significant figures. Leading zeros are defined as zeros that come to the left of a non-zero integer, and they are never significant. For example, if I make the measurement 0.0027 liters, the 3 zeros to the left of the 2 and the 7 are leading zeros. They're not significant, so only the 2 and 7 are significant, so this measurement only has 2 significant figures. A nice way to remember this is that if you convert the measurement from decimal notation to standard scientific notation, and you get 2.7 times 10 to the negative third liters, where did those zeros go? They went away. They can't be significant if they disappear when you convert them from decimal to scientific notation, so that's only 2 significant figures. Actually, they didn't disappear. They went into the power of 10. Captive zeros are always significant. Captive zeros are zeros that come between non-zero integers. So for example, the measurement 809 grams has 3 significant figures. That 0 tells me it's not a 9 and it's not a 1. I trust the information it carries, so it is significant. Trailing zeros, though, are significant only if there is a decimal point in the measurement. And a trailing zero is a zero that comes to the right of a non-zero integer. So for example, 4.10 meters, the decimal point in that measurement tells me I trust the 0. It's not 4.09 meters, it's not 4.11 meters. That 0 carries meaningful information, so that measurement has 3 significant figures. Finally, exact numbers are infinitely precise and have unlimited significant figures. What are exact numbers? Definitions and counting numbers. So for example, 12 inches per foot. How do we know there are 12 inches in a foot? We define it as such. Therefore, that number has unlimited precision. Counting numbers, if I look and I see that there are 16 students in this section, then I didn't use a device to measure that. I simply counted objects. That number has unlimited significant figures. So let's do some practice assigning significant figures to measurements. On this page, I have a whole mess of numbers, and we're going to systematically assign the number of sig figs in each. 3.78 grams, each of those numbers is a non-zero integer, so that has 3 sig figs. 0.0029 meters, those are leading zeros. They are not significant, so that measurement only has 2 significant figures. 5.04 liters, that captive zero is significant, so that has 3 significant figures. But if I measure 5.0040 liters, I've got 2 captive zeros that are clearly significant. The trailing 0 at the end, because there's a decimal point in the number, it becomes significant, so this measurement actually has 5 sig figs. 0.06030 millimeters, look, all sorts of zeros. The leading zeros are not significant, but the captive 0 is, and the trailing 0 is significant because there is a decimal point, so this measurement has 4 significant figures. If I measure a quantity of energy as 400 joules, all I know is it's not 300, it's not 500, it's closest to 400. I don't trust those zeros, so this only has 1 significant figure. But if I measure it with a device that lets me distinguish between 399, 400, and 401, I indicate that by putting a decimal point after the 0, so this measurement has 3 significant figures. 1.2 times 10 to the third seconds, ignore the power of 10. The precision is only reflected in the first part of the number. So 1.2 has 2 significant figures. 1.20 times 10 to the 8th, again, the power of 10 doesn't matter, but now, because there is a 0 and a decimal point, this measurement has 3 significant figures. 1.200 times 10 to the 8th has 4 significant figures. Actually, counting significant figures when a measurement is expressed in scientific notation is easy because the number of sig figs is simply however many numbers are in the first part of the expression. So all of this leads to the question, why does this matter? Well, when you go into the laboratory and make a measurement, you don't just record that measurement, you use it to calculate a quantity. Okay? So let's review using significant figures in calculations. Suppose I want to measure the velocity of an object by measuring the distance it travels and the time that it takes. And let's say that the distance is 22.5 meters and the time is 6.5 seconds. Okay? So I'll plug in 22.5 meters over 6.5 seconds. perform the calculation, and I get 3.461538.462 meters per second. Now, do you really get to keep all those digits? Absolutely not, okay? You started with measurements that had 2 and 3 significant figures. Are you going to tell me your result really has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant figures? No. You need to round the result because, and here's the important idea, the result of the calculation cannot be more precise than the least precise measurement used in the calculation. So here's how we would round that result. When multiplying and dividing, round the result so it has the same number of significant figures as the initial measurement with the fewest number of sig figs. 22.5 meters, the distance has 3 sig figs. 6.5 seconds, the time only has 2 significant figures. So that means I'm going to round this to 2 significant figures. So this becomes 3.5 meters per second. Now, a word about unit conversions. Let's look at a couple of unit conversion problems. 37,500 meters multiplied by 1 kilometer over 1,000 meters gives me 375 meters. 175 pounds converted to kilograms gives me 79.37948 kilograms. Now, let's look at the first problem. 1 kilometer over 1,000 meters, that's a definition. And we said as an exact number, it has unlimited precision, so that means I round to the same number of sig figs as my initial measurement, which is 3 sig figs. However, 1 kilogram over 2.2046 pounds is not a definition. It's actually a measurement because it's between different systems of units, kilograms being the SI system and pounds being the English or American system. But look at that conversion factor. It's got 5 significant figures, whereas my initial measurement only had 3 significant figures. So I will round this also to 3 significant figures, so this becomes 79.4 kilograms. So when you're doing unit conversion problems, your conversion factor is either a definition, which has unlimited significant figures, or if it's between 2 different systems of units, it's got lots and lots of significant figures. So the rule is round to the number of sig figs in your initial measurement. Finally, let's talk about rounding when we are doing addition or subtraction problems. Suppose I measure 2 objects. One I measure as 26 centimeters, and one I measure as a length of 3.3 centimeters using a more precise measuring device. I add them together and I get 29.3 centimeters. Now the question is, do I really trust that 3? I don't, because the first measurement, 26, was only made to the nearest centimeter, not to the nearest tenth of a centimeter. I don't know what comes after that 6. Therefore, I'm going to express this simply as 29 centimeters. Okay? So the rule for adding and subtracting is somewhat different. Round the result so it has the same number of digits after the decimal point as the initial measurement with the fewest digits after the decimal point. So it seems kind of strange that the way you round depends upon the type of operation you do, but that is the way it works. So just to reiterate, when multiplying and dividing, round the result so it has the same number of sig figs as the initial measurement with the fewest sig figs. But when you're adding and subtracting, round so it has the same number of digits after the decimal point as the initial measurement with the fewest number of digits after the decimal point. And in our next video, we will review rounding. See you then.